Our technical session on ocean technology. We'll have 4 papers in this session. And just a reminder to all presenters, you have 27 minutes to leave 3 minutes for discussion and questions. Even if you can make it shorter, it's not a problem. We'll have more interactions. But please, you have a sign on your time is finished. So the first presentation will be by Professor Yasuyuki Ikegami from Saga University in Japan. So please, floor is yours.
It's my pleasure to introduce Professor Ikegami. He is not new to NIOTians, but for completeness sake, I'll introduce him. Professor Ikegami is currently working as Professor, Deputy Director, leader of OTEC division in the Institute of Ocean Energy, Saga University, Japan. He is working as delegate of Japan on executive committee members of International Energy Agency, Ocean Energy Systems, that is IEA OES from 2003, and works as coordinator of PASK on status of OTEC and its resource assessment in IEA OES from 2016. Professor Ikegami.
Good morning. So, thank you for Chairman. So, I'm very honored to be here because we have honor to the long time history with NIOT and Saga University. So, NIOT made a big history of the OTEC. So, without NIOT OTEC project and LTD dissemination, they are not active in the world now. So, very important NIOT OTEC and LTD achievement. So, I'm happy to attend this celebration. So, we would like to explain the blue innovation using OTEC and DOA, deep sea water application by international collaboration. So first we want to introduce history. Sorry, this age is a mistake. 1997. Sorry. Dr. Ravindran first time visited Saga University. This is a memorial photo. This is Japan's OTEC founder, Professor Uehara. So we hold the international OTEC symposium in Saga, 1999. Dr. Furima and Jayashankar presented in this seminar. So they are good memories for me. And this is the 1 megawatt OTEC intake tube. I took the photo inside the OTEC tube. OTEC researcher want to take a photo inside the intake tube. So we are happy to drinking the desalination water of the floating LTD. Very tasty desalinated water. So first we would like to explain our institute. Our institute, 45 years of the research, especially thermodynamics and OTEC. 1973 started by Professor Uehara. And we have an experimental apparatus, 30 kilowatt OTEC and 25 kilowatt OTEC, using ammonia water mixtures and heat exchanger testing. And education, we are annually international program, the seminar and the platform for the young researchers. So I invited from the NIOT's young researchers. So, and we have a satellite, Imejima satellite. This is the OTEC power plant, 100 kilowatt. And we are desalinated plant, small plant, and hydrogen production plant. After OTEC electricity, we desalinated water and hydrogen product by OTEC electricity now. So this OTEC plant started April 2013. So world first OTEC demonstration success in the second boom. What means second boom? Later I'd like to explain. 100 kilowatts generator, working fluid or R134A, and connected the post-OTEC this project, and connected the commercial electric companies, grid, and 60 years continuous operation, data and actual seawater. And as you know, US, after the US added 5 kilowatt, so 105 kilowatt constructed and generated electricity. So after 2013, US started world's largest OTEC power plant to the connected US grid. So this is the number of the OTEC international patent application. After oil crisis, OTEC is the first boom. After that, oil price down, so OTEC, many projects stopped and postponed. So, but recently, the second boom, Japan, US, and so on, many strongly progress. So world progress in US and French, of course India, Korea, and Netherlands, also Japan. So this is IEA, International Energy Agency, shows the ongoing OTEC project. 10 years ago, only one project, but recently, there are many projects, operation and planning and so on. Why now is the OTEC in Japan's world? First reason is technology improvement. Next, stable energy. As you know, base load energy. So, 2 years ago, in Fukushima, stable during 30 years, among the weather, or suddenly snow, temperature decreased, but ocean temperature increased. So during the snow, so Fukushima can operating stable. And technology improvement. So as you know, 70 and 80 years, so many projects have started. Evaluation in 90s, 80s, OTEC is technical feasible, but not economical. So many projects postponed and stopped. But recently, spotlight again due to the technological improvement and change to the social situation. So, what is the technology improvement? Or new cycle invented. So, previously, Rankin and Karina, Saga, and so on. Recently, many cycle developed. And technology improvement, commercialized power plant using small temperature, similar OTEC technology applied to the many projects, 3 megawatt, 2 megawatt, 4 megawatt, so on, for the invested energy. So technical development in the floating structure and offshore drilling technology is becomes advanced. So, and special heat exchanger for the OTEC developed, supported by Japanese government. But unfortunately, the not yet commercialized of the OTEC. As you know, so technology is the barrier of the base. So basic research is success. Commercialize is possible as commercialize, but this potential develop and scale up is difficult. So this is this barrier. So we have to reach to the to the basic to the commercialized. So in Japan now in the challenge to the advanced technology, we want to introduce the recently Japan challenge to the new technologies. So first, new plate for the heat exchanger. So this is the total cost. OTEC is a heat exchanger occupies a very, for the total cost very large, 1/4 and 1/3. So after optimize, we decrease heat exchanger cost. So recently we developed a new heat exchanger, plate heat exchanger. Normally with conventional surface, smooth surface used, but recently we developed a special surface for the evaporator and condenser. This engineering novel from the long time ago. So, but conventional special surface added the particle after the press. But this press is immediately we can press on the surface. So, this engineering not increasing the cost, but heat transfer coefficient increasing. So this is a performance test, evaporator side, condenser side. This is a smooth and pop dot and herringbone plate configuration. So pop dot configuration is increasing 23%, but condensation is pop dot not increasing. This is a herringbone plate is a 20% increase in heat performance. This meaning we can decrease the heat exchanger cost about 20%. So next we want to explain the multi-stage OTEC cycle, double ranking cycle. So as we know, so conventional ranking cycle, pure ranking cycle, and next we challenge the mixtures. But if you mixtures used, so some cases heat exchanger performance, heat transfer coefficient decrease. So we want to challenge the double ranking cycle. So double ranking cycle increasing this output. So double stage ranking cycle after OTEC use warm CO2, after that we use the next OTEC cycle. So we can get this area added the per output. So theoretically we analysis power output of the multi-stage ranking cycle. So this is a single stage. So we can increase in the 20% and 50% increase in the output. So third, new plate type heat exchanger, cross flow type. So conventional plate type heat exchanger is counter flow and parallel flow. But we developed a cross-flow heat exchanger for the double ranking cycle. This is a water flow, seawater flow, the working fluid flow. So if we use the counter flow for the multi-stage, so pressure drop increasing because this is a seawater path is longer. But if you use cross flow, we can decrease path of the seawater. So all new technology applies Kumejima Otek power plant. So finally, we Kumejima Otek demonstration net power efficiency about 60%. 60% net power decrease working fluid, seawater pump, or seawater pump. So from this data, we can expect it Otek net power efficiency 50 to 80%. So for this demonstration plant, we are objective power generation demonstration test establish Otek system for the applies 1 mega 10 mega Otek using the facilities and estimation of the margin deep sea of the using system. So this is an experimental result of the evaporator. So this line is estimated values approximate expression, but this is experimental data. Experimental data about 10% increase in the prediction. So biofouling, so not occurs condensation side and evaporation side, not chemical treatment. So summer efficiency, this is compares 1 year summer efficiency. So almost 5% increase in the estimated value. So from the this Otek 100 kilowatt plant to apply the commercial plant. So from our experimental data applies 1 megawatt Otek and 10 megawatt floating Otek. So after that, we designed using Kumejima Otek power plant data. 1 megawatt on one type, 10 megawatt type. So now we are planning the commercialize in Japan. Next 1 megawatt on one type, then 10 megawatt offshore, finally 100 megawatt. So we can get approvable. Nippon Kaiji Kyokai issues the first approvable in principle for the totally submerged of the floating power plant of the Japan Marine United Corporation. So as a potential Otek byproduct. So as you know, this century, 5 big issues: energy and environment, and population issue, food issue, and water issue. So UN now announcement sustainable development goals, 70 goals. So Otek is contributed not only electricity, not only clean energy and fresh water and aquaculture and so on. Many contributed by Otek for the sustainable development goal. One was a challenge in Japan, promoting seawater resources using deep seawater, Takumi project. So deep seawater including nutrients. So after mixed seawater, cold seawater, so discharged, then recover the fish resources. So this project trying to Tokyo, Sagami Bay. This is a Mount Fuji. This is a floating type. This is people. So this is a mooring system, single point mooring. So this is an intake tube before the mooring. So 5 years of operating. Sometimes typhoon coming, but stable the operation. So and Kumejima, the post-Otek generation. So we promoting deep sea application. So in there, this figure shows Otek potential in Japan. Unfortunately, limited areas, southern sea water in Japan. This is here the Kumejima and Okinawa. So Okinawa has high potential, similar to the already installed OTEC, but Okinawa Prefecture planning the 10 or 20% using OTEC future plan. So in Japan, 16 site deep sea water intake tube already application over the 20 years. So this is a deep sea water used in Japan capacity all site. So Kumejima is the biggest, 13,000 ton per day desalination. So in Kumejima, over the 20 years continuously operating deep sea water. So occurs a new industry using deep sea water. So before the deep sea water industry, so sugarcane industry biggest industry in Kumejima because 8,000 island people population. So, but this deep sea water industry is bigger than sugarcane, twice big market than sugarcanes. So recently increasing 25 million US dollars. One of the industries shrimp. Shrimp is now number one in the product in Japan because in deep sea water very few bacteria. So shrimp is very healthy and safety. So this shrimp is very become the biggest industry in Kumejima. And next is the sea grape. Sea grape is number one product in Japan because sea grape is for the summer hot water needed, but too much hot water is quality is poor. So already we have to control the 24 temperature. So Kumejima can control the temperature. So this market is grew up. This is a sea grade. 24 is high quality. 30 is poor. Too much grew up, so poor the tasty. So and spinach. So spinach have to control the temperature, but Kumejima is summer is the hottest, close to the over the 35 temperature centigrade. But only land cooling pipe. Outside land is a high temperature, but this is a land is a cool. So in summer, Kumejima can produce the spinach. So now already commercialized. This is already commercialized. So now Kumejima next plans 10 times OTEC plant, 1 megawatt OTEC. So after that, byproduct promoting 7 times commercials we expected. So recently we get a new fund, SATREPS, in Japanese government international collaboration project. So this SATREPS project contributed SDGs. So in this project, we challenge the hybrid OTEC, desalination and OTEC. This LTDD already achievement by NIOT, so good achievement. So and OTEC the already achieved good success in Kumejima. So we want to join it, this system. So hybrid OTEC system is we challenge the new hybrid. So surface seawater flash evaporation here. So this steam go to the evaporator, not the condenser, evaporator. So ammonia evaporating by this fresh water. So this ammonia go to the turbine generator. This is a conventional text system. This is a conventional ADDD. So we developed a new heat exchanger because this side is condensation. This side evaporation. So new type heat exchanger have to develop in this project. But this benefit, before this hybrid cycle, we have to use titanium. But in this new hybrid OTEC system, we can use aluminum or stainless, not titanium. We can decrease the cost. And this path is fresh water, so there are no occurs biofouling. So we can decrease this is the evaporation cost and the desalination cost. So now we are new model, not Kumejima model. Kumejima model uses the conventional Rankine cycle or double Rankine cycle, but this new model we use the hybrid OTEC system, combined desalination and OTEC system. So now we are planning. So 2002, we are installed the hybrid OTEC system in Malaysia. So this is the OTEC cost. So OTEC cost is large OTEC cost very economically, but small OTEC cost is very higher than conventional plant. So, but this 1 megawatt applies the island electricity. But if you join it deep field application, we can decrease electric cost because we can share the intake tube cost. Intake tube cost very higher than another cost. So if we join it, decrease total electricity for the small OTEC plant. So after subreps, we are promoting the 1 megawatt, 10 megawatt, 100 megawatt. So we want to contribute it for the sustainable our supplies by the blue revolution from the Japan and India. So thank you, arigato, nandi.
Thank you to be on time. We have time for questions, so please.
Professor Ikegami, very interesting talk on the latest position of combining OTEC with other applications like heat water, cold water, desalination, etc. Very, very interesting. And the improvement in the heat exchanger by about 27% also is very interesting. I think we have a very good cooperation with the industry to make new heat transfer plates. Are we making them in aluminium or what is the plate heat exchange material? Titanium?
Now titanium. Yeah. So, but we can make stainless, or so we can apply the another material. So, but hybrid OTEC system, we apply the stainless. Yeah.
And also the cross-flow system we have introduced, does it have enough heat transfer for the seawater because it's a very short length?
Yeah.
Are you able to achieve a good heat transfer quantity?
Yeah.
With the short length?
Yeah. Very important.
Very important.
Yeah, very important your question. So we have to design the, as you said, this water side is wider, so velocity decrease. But we can have to optimize this balance. Yeah.
Okay, that's very, very interesting. And the surface roughness is only by pressing. There is no extra spraying of material. The surface roughness you create.
Yeah.
It's only by pressing with the rough surface.
Yeah.
There is no extra material spray.
No, not spray.
So.
So if we straight. So heat transfer coefficient increasing,
Yes.
but cost increasing.
Yes, yes.
But this method is not
Yes.
increasing cost.
Very
Because
interesting.
the on-time manufacturers. Yeah.
Very interesting. Congratulations, yes.
Short question, please.
Okay, extremely good talk. Now, when you believe that OTEC would be able to compete with other conventional sources, what is your future projection? And also, what is the total potential of OTEC energy in and around Japan?
So, unfortunately, not yet officially Japan government roadmap. Now only development stage. Yeah, but now after Fukushima success, so we need, now new planning now. Yeah.
I'm afraid we have to stop to keep on time. Thank you for the presentation. It was realistic and futuristic at the same time. We have to go on to keep on schedule. And the next paper will be given by Professor David Ingram from the University of Edinburgh in the United Kingdom.
Professor David Ingram has completed his PhD in computational fluid dynamics from Manchester Metropolitan University in 1992. He is currently the head of the Institute for Energy Systems and since July 2011 has been the director of the Industrial Doctoral Center for Offshore Renewable Energy. He is a member of the Joint Research Institute in Energy, part of the Edinburgh Research Partnership funded by the Scottish Funding Council and fellow of the Institute of Marine Engineering, Science and Technology in 2009. Proceed.
Thank you. So, I'm going to talk about tidal turbines, so something slightly different from the OTEC that we've just been hearing about. And as all of these things, it's not the work of just me, but there's quite a team behind the work that I'm going to present. And actually, I'm going to say very little about computational fluid dynamics and quite a lot about experimental work and ocean measurement. So I'm going to talk about two projects. One project that's taken place in the Orkneys, and then I'm going to talk about the work we've done in Edinburgh, combining that. And I should say as well that the work in Edinburgh is related to a project in which NIOT is a partner. And then I'll talk about what we're doing in Ushant, as we would call it in English, or Western, I think it is in French, some islands just to the west of France. So, just to say something briefly about the University of Edinburgh, we were founded in 1583, the sixth oldest English-speaking university in the world, and we have a combined School of Engineering, and last year we celebrated 150 years of the Regius Professor of Engineering, so Chair of Engineering, was established by Queen Victoria. This is a very beautiful old college building in the middle of Edinburgh where engineering is not based. We're out in some more modern and less pretty buildings. This is a photograph from 2014, just to show that I've been to NIOT before, but I can't show as many photographs as some of the other speakers. I've been here twice before, and I don't have a photograph from the earlier visit. Just to say something about the Institute for Energy Systems, we're a multidisciplinary institute that spans low carbon and zero carbon energy, and we have about 25 members of faculty, about 40 postdoctoral researchers, and about 120 PhD and engineering doctoral students. We work on energy systems, and here is a schematic of an energy system. This happens to be a tidal turbine, but it could be any other renewable energy system. And we start by trying to understand what the resource is doing, either by measurement or by modelling, and I will talk a little bit about that later on. And then once we've done that, we try and characterise sea states that we want to conduct tests under, And we do fundamental work on fluid structure, interaction. This is actually PIV measurements. We build electrical machines, so this is a 1 megawatt direct drive rotary machine and a linear machine. We work on power electronics because you have to understand how these machines will interface with the grid. We look at how that grid behaves in a smart way. And we also work on energy storage, and we have 2 teams working on high temperature energy storage. We do work on carbon capture and storage, but from a power station perspective, not from a chemistry perspective. And we work with end user communities to try and understand how we could do this in a way to help off-grid communities and communities that rely on diesel. These happen to be some photographs from a trip to the Sunderlands in West Bengal, where we've been looking at tidal turbines. And underneath all of that, there's a policy and innovation group, and this is led by Henry Jeffrey, who is known to quite a few members of the audience here because he's the current chair of the IEAOS. We have the Flowwave Ocean Energy Research Facility, which is a unique wave and tidal test facility. It's one of 2 circular wave basins in the world, and it's the only one that generates wave and tidal currents from any direction. And I will show you some results from some experiments we've done in that. Okay. So we want to understand what devices are doing in the real environment. We want to design things so that they last, so that they're reliable, so that they operate for a long period of time, because that's the only way that we can make things economically viable. And in order to do that, we have to bring together measurement, hydrodynamic modeling, we have to characterize and do a lot of data processing, and then we want to come up with engineering tools that will improve the design for future technologies. We've done this through 3 different projects. The REDAP project was a commercial project based around a commercial 1 megawatt turbine. FlowTurb is the project that NIOT is involved in. And then we're working on a project at the moment called RealTide, which is the project in Ushant. So in REDAP we took a lot of measurements. This is in 50 metres of water, and the spots on this diagram show all the different places that we've got measurement instruments, and you collect a lot of data. Just to give you an example of trying to do this, this is a highly tidal environment. The current flows at 5 or 6 knots, and you've got to put stuff down. So if we're putting down a small ADCP, then we have to embed it in about 2 tons of concrete, otherwise it doesn't stay where we put it. So we've got a lot of concrete frames, you need a lot of work boats, and you'll see that we also mount the devices on gimbals because the floor is not level. So there's ADCP on gimbals. We also find a problem with ADCPs in that they're an oceanographic instrument and they integrate the flow over a very wide area. So we've been working to develop a convergent beam instrument where we build something a bit like a Vectrino that you might use in a laboratory, but at a scale that we can deploy in the ocean. We did this successfully in the REDAP project, and we're currently working on a new version of the instrument which will be steerable. So we're using single beam instruments which we have manufactured specially for us. When you interface these things to real equipment, you have to work very, very closely with the technology developers and with the certification agencies, and we went through about 15 iterations of the design to mount it on the 1 megawatt turbine before we had something that everybody was happy with. So that's a lot of work and a big problem. And then you measure the data, and you need to understand what the waves are doing, what the tidal current is doing, what the turbine is doing, and you end up, I think after 4 years and about 20 different deployments of instruments, we have about 4 terabytes of data. And that's quite a lot, so we need to do something with it. So data management is a problem. We heard yesterday about the FAIR data principles. I just want to show you briefly what we do. So we want to search the data and to come up with meaningful results. We're working on a public tool for this at the moment, so that we don't have to spend hours scratching our heads and running hundreds of MATLAB scripts. This is an example of long-term data where somebody wanted to know what the turbulence intensity on the site was, and so we processed the entire set of data that we'd measured for the whole campaign, and that led to some journal publications. But equally, you have problems where somebody wants to know about instantaneous velocity variation, and so you're looking at a very small period of data, and you've got to quality assure that. So, just to show you the scariest video that you'll ever see if you're a tidal turbine developer, this is measured data from the EMAC test site. It's in 40 metres of water, the turbine's about 20 metres in diameter, and it's in the middle of the water column. Those are quite moderate 4 metre high waves for the site. And the velocity is varying by more than 1 metre a second at the turbine hub height, and there's a huge shear caused. So this is going to cause a lot of issues for our turbine. There's going to be a lot of unbalanced loading on the turbine, a lot of forces and moments that we need to know about so that the machine doesn't break. I've only got point measurements, so one thing that we do that's very important is to use those point measurements together with shallow water models and various tidal models to give us a broader area information. So it's another use of the field data that's been measured. The other thing that we do is we post-process this data in a way that we can put into the test tank so that we have realistic sea conditions which we are conducting in the tank. Now all of this is measuring velocities, but what we really care about is forces, because we want to predict the forces on the turbine, because that's what the engineering designers need to know about. And just to give you an example of this is some graphs that show the tide or velocity variation at different states of the tide for the flood and ebb tides at the EMAC site. And if we put a turbine in the position that the Alstom turbine, a floating turbine in, then this is the kind of velocity variation that the turbine would see. If we look at the turbine that was actually deployed, the Alstom turbine, then this is what we see. And if we look at something that's mounted on the sea bottom and is close to the bottom in, say, the open hydro turbine, then this is the kind of thing that it will see. In each case, you see different mean velocities, but you also see completely different variations in the velocity. Okay. So we wanted to do some experiments, so we built some model turbines, and I want to stress that these turbines are really dynamometers. They're not designed to generate power other than to control the systems and to measure the forces. They're 1.2 meters in diameter, and we have 3 of them. So we start off by trying to understand what the test conditions are that we need to recreate, and we have a problem. The problem that we have is that you measure a wave spectra, and then you impose that wave spectra on a current, and it's transformed by the current. So you need to understand how that transformation takes place, and we've spent a long time scratching our heads to try and get that kind of information together. And then we can look at a lot of measurements in the tank to understand what the flow is doing. So these are different turbulence spectra and different water depths for different sets of sea conditions in the tank. And then you take your turbines, so we have a motor, we have a slip ring, we have a huge amount of measurement data. We're taking the measurements as close to the nose of the turbine as possible. We're measuring blade bending forces, we're measuring thrust and torque. And then you can put a single turbine in and you can do some experiments, and you can measure loads on that turbine under different conditions. So then you can produce a spectrum of the forces on the turbine. This is using constant torque control, and we can identify different things. So where is the blade passing the tower, where are the wave excitation forces, and so on. After that, we did some array tests. This was the first set of array tests that we did where we just put the turbines together in an array. We have recently been redoing these tests. So this is our technician putting everything together. And there's the turbines ready to go. And in the second set of tests, the turbines have been electrically connected. And this electrical connection is very important because they're connected to a grid, the generators want to synchronise. So the turbines want to try and rotate at the same speed. The local hydrodynamics means that they don't want to rotate at the same speed, so you get completely different forces from those that you measure if you just have 3 independently operating turbines. So here we are, this is the turbines under waves and current. This is with waves that are opposing the current in the test facility. And this is what it looks like from above. And you can see that the waves are steepening and shoaling and breaking over the top of the turbines. And these are actually very similar to the conditions that I showed you the ocean measurements of at the beginning of the talk. So we want to bring it all together. We need to understand the interaction of devices in the real environment and the electricity network if we're going to improve engineering design tools and reduce risk. If we reduce risk, we reduce the price of the projects, and then things start to become economically viable. So I'll talk a little bit about modelling. This is some detached eddy simulations which we did in conjunction with the Pontifical Catholic University of Chile and the student project. So this is using an actuator disk model of the turbine. We've now got an actuator line model running with them. And this is an actuator line model which has been running for the real-time project using the NREL SOFA software and open phone. What we're trying to do next with those models is to put a full electromechanical model behind them so that the speed of the rotor in those simulations is an accurate representation of what the speed of the rotor would be on the real turbine, and so that we can put in network effects at the network end and see how that affects the performance of the rotor. And we intend to do the same thing with an array experiment later this year. So, the last thing I want to talk about is measurements in the Fromberg Strait and Ushant. This is part of the real-time project which we're doing with Sabella turbines, and that's the Sabella machine behind some of the participants in the project. We've used our ABCP instruments, and if you're going to start putting these on a turbine, then you need to end up designing power supply units and putting them in pressure vessels. And this is an interesting story because it's very easy to go and buy a very expensive pressure vessel that's rated to a couple of thousand bar, sort of 6,000 metres and all this kind of stuff. We want something that goes into 50 metres of water. So we can't afford that expense. And the other problem is that in 50 metres of water, then you feel the effect of waves on all the seals. So we found things failing much more quickly than they're supposed to fail. And that's a problem. And then you install them on the turbine, and if you're very lucky, the turbine manufacturer allows you to drill holes in their machines, put the instruments in, and you've got to put the instruments into the turbine in the spaces that are left, so you end up working in quite cramped conditions. And you also end up working to a very tight deadline, because that turbine is going in the water on a particular date when the weather is right and the ship is there that's going to do it, and you're not allowed to delay that launch. So that's an interesting problem. So there's the instruments installed on the turbine and checking that they're level and in the right positions. And then the turbine was lowered into the sea, and that's quite a nice day when that's happening. This is a very famous photograph of a lighthouse in a storm taken by an amazing French photographer of lighthouses, and that lighthouse is very close to the deployment location of the turbine. So this is what the sea conditions are like on not a nice day. And then we had a problem. And this is an example of this launch fever problem that you don't think about everything when you're trying to get everything ready. So this turbine was going in last September, and there was this 2-amp fuse. We've kept the fuse, and it's going to be encased in resin with a little plaque on it because it caused us so much problems. We had to take power from the turbine to power the instruments, and there was a hard 2-amp fuse in between the turbine and the instruments. And we all forgot about it, And when we switched the instruments on, they drew 12 amps. So the fuse blew, and we got no data over the last winter. Fortunately, the turbine is out of the water again, and we've been reworking all the power systems and sorting everything out. Even if the turbine had stayed underwater, we would still have managed to get data this summer because divers were going to go down and retrofit the system to power our instruments. But the turbine came out, so we've been doing this on dry land. So I wanted to sort of conclude with an important message. I always thought this was said by the Duke of Wellington, but it turns out that it was a German general during the Napoleonic Wars. No plane ever survives contact with the enemy. If you have been involved in any kind of marine energy developments, and I'm sure this also applies to OTEC, then you would actually say no plane ever survives contact with salt water. We have to be very careful about understanding what's going to happen when we put our machines into the sea and our instruments into the sea. And that leads to the comment that Professor Stephen Salter, the father of wave energy at the University of Edinburgh, who started working on this in the 1970s, said, "Don't go to sea until you think you have nothing to learn by doing so." So I would urge people to make all their mistakes on dry land and behind closed doors and at the smallest scale that you possibly can. So understanding dynamic loads is critical to the design of reliable marine energy devices, and reliability reduces those maintenance costs and increases the service intervals. This lowers the levelized cost of energy and increases investor confidence. And that's all I wanted to say, other than to thank the vast number of collaborators, and I see that I forgot, NIOT is on there, and also our very generous funders who funded this work over a period of about 10 years. Thank you very much.
Thank you, Dave. We have time for question now. Please. Hi.
I think my voice is quite loud.
But they are recording. This is what. Thank you.
Thank you for a nice presentation, and very interesting. Especially, you go through the same experience we have whenever we go to the sea, the unaffected problems and the small things like this, views and all that. We have had many experiences like that. Yeah, we appreciate your problems very well. I just have one question about the turbine design, because the turbine design, turbine is exposed to different velocity and pressure conditions over the height.
Yeah.
And how complicated is designed for reversible flow, because when between the air flow and flood flow, there's a reversal of velocity. And we have I am sure that you have a great pitching facility. And how much is the turning? Are you taking care of the directional reversal?
Absolutely. So in the test facility, we're able to generate current from any direction. That's one of the things that's unique about it. And so it was actually designed to give us a reasonably sensible boundary layer profile and rather than a plug flow. And so what we do is we'll leave the model there, we'll leave the turbines in the same position, and we can make the tide go in the ebb direction. One of the things that's interesting to note is that when you look at a lot of these sites, the flood direction might be in that direction, but the ebb tide might go that way. So they're not 180 degrees apart. And one of the common mistakes that developers will make is they will assume they will be 180 degrees apart. So it's something, again, that you need to know a lot about the site that you're deploying in. And I think the message that I would really like to get out of this for everybody is that if you're going to go and put a turbine in the sea somewhere, the first thing you should do is put a lot of instrumentation there and take a lot of measurements.
Is it a simple airport profile, or is it a like this or something like this?
So these turbine blades are a simple not a very simple aerofoil, but they're the same aerofoil section all the way along the length. they were scaled down from the blades that are on that 1 megawatt turbine that we used. Now, the interesting thing about blades is you can't scale them geometrically, so we had to get blades redesigned that were for the 60 centimetre chord span length that they have, so that they have the same thrust and torque characteristics for TSR as the full-size blades do. We've tested other blades on the turbines as well, but these were designed to be very simple, not to be a realistic machine, but to be something that we could learn a lot of lessons with.
Thank you. Very interesting. Now, influence is special area of design and development. Thank you.
Any other question? Okay, there's one question.
So what are being done here? What is the diameter of the turbine? Can I have an idea?
Yeah, so our model turbine is 1.2 meters in diameter. The full-scale turbine is 16 meters in diameter.
Thank you.
Any more questions?
When do you expect that the final result is not?
Well, we're hoping that the turbine will be back in the water later this month, but it depends on the weather. So there's a weather window at the end of this month, and there's a weather window in September. So at the moment, we're in the hands of the meteorologists.
I'm clearly not an underwater current power guy, so this is a naive question. But in the aircraft industry, one of the things that's happening is as we start thinking about how you would build an electric aircraft, the advantage of having a lot of motors rather than an individual motor has enormous advantages in terms of reliability and also aerodynamically. So I'm just kind of curious, so all of, you showed that picture of the turbine in a current environment where there's a fair degree of variability vertically, and presumably in time as well. Is there any advantage to lots of small turbines? I mean, if the electric motors were scalable in a manufacturing sense, would you design that differently?
So I think this is an area where the jury is out at the moment. There are a couple of designers who've been looking at a very large number of small-scale rotors. So they say, why don't build a megawatt-scale machine? Use 10 kilowatt turbines and have 100 of them in a frame. Now that's okay, but your probability of failure has just gone through the roof, and you have a maintenance issue. So you might say, well, okay, I've got 100 turbines, I'm not going to maintain anything until 30% of them have failed. But you're also dealing with a very large piece of kit, so getting that in and out of the water can be more complex. On the other hand, it may have more efficiency than a horizontal axis turbine. I would also say our turbine's got 3 blades. The turbine that we modelled had 3 blades. I actually think that a 3-blade horizontal axis tidal turbine just shows that you didn't think about the problem properly. And there is no reason why they should have 3 blades. They could have more. The Sabella one, I think, has 5, or they could have less. The tidal the CGL turbine that was tested for 10 years in Northern Ireland was a 2-bladed machine. But you need to think about how many blades you want from an engineering design point of view.
Thank you.
Thank you very much, Dave. We now move to the next presentation by Dr. Emmanuel Platzgummer from Ifremer in France. Please, Emmanuel.
Dr. Emmanuel Platzgummer graduated in political studies with a strong emphasis on international relations and cross-cultural issues. Currently, she is working as International Affairs Officer in IFRMA.
First, to really wonderfully thank NIOT for the wonderful hospitality that we enjoyed for the 2 days, and thank you again for all the team. And I am very thankful also for the opportunity today to make this speech and to talk in front of such a distinguished audience. What I would like to do today is just to give you an overview of IFRMA, with a general presentation of what our institute is doing today, and give some highlights of our operational facilities. And I will also take one particular example to show one marine observatory that we are very much involved in. So to begin with, the history of IFRMA is the merger of two worlds, that of marine fisheries, which crossed paths with the development of oceanography and in France, so hence the world of ocean exploration. So nowadays, IFRMA is an integrated research institute covering all marine sciences and ocean-related technologies. Thus, we cover a broad range of activities in research, engineering, and transnational projects coordination. Our goals are to study and assess the ocean's resources and the sustainable use, improve methods to monitor, forecast, and build stewardship to protect the oceans and enhance the value of marine and coastal environment. Our mission is also to foster the socio-economic development of maritime sector. So IFRMA is under two ministries in France, the Ministry of Research and Innovation, and the Ministry in charge of Environment. So we have a staff of about 1,500 people. So the missions endowed by the French state are fourfold. First is to enhance marine science knowledge in order to better understand, preserve, and exploit ocean resources. So this is why the Institute initiates joint projects targeting research infrastructures like fleets, observatories, and databases. Second, our mission is to deliver expertise and produce environmental assessment on water quality and fish stock. So there are entire services at IFRMA which are dedicated to provide scientific support for public policies, both at national level, for French state, and also at European level. For instance, we provide expertise for the EU Common Fisheries Policies, as well as the Marine Strategy Framework Directives. Third, we also perform applied research and work together with the industry for technological advancement and innovation. And by doing so, we encourage technological and industrial developments in numerous fields, in underwater operations, instrument systems, mineral and energy resources, fisheries, and aquaculture. And fourth, but this is really the backbone of all of it, we operate oceanographic facilities, such as the National Research Fleet and ocean observatories. I will come back to that a bit later. And IFRMA contributes significantly to the development of the operation of French and European marine research facilities. All in all, IFRMA represents about 50% of the French national effort in marine sciences. And to enlarge a little bit the picture, I just want to remind you that France occupies an important position in the maritime sector, And one reason for that is that we have the second largest maritime area in the world, after the US. So you can see on the map in blue is the French economic exclusive zones that were in all the oceans. Atlantic, Pacific, Southern Ocean. So this territory holds substantial potential in terms of discovery, innovation, economic growth, and resources for sectors with high social stakes like energy, food, and health. But on the other hand, this marine environment is also experiencing ever-increasing pressures, like high demand for raw materials and marine source food, expanding coastal populations, marine pollution and litter. And in light of global change, increasing our knowledge in marine sciences is essential for the sustainability of our planet. So translated into IFREMER organization, so we have a planet-wide presence in the Atlantic Ocean, South Indian Ocean, Antarctic, and the Pacific Oceans. So our headquarters are in Brest, in Brittany, in France. We have 5 main centers. 4 are in the Hexagon. Hexagon is what we call France because we have 6 sites. So one one center is in the North and the Channel and the North Sea in Boulogne-sur-Mer. We have another big center in Brest, in Brittany, the other center in Nantes on the Atlantic shore, and the fourth one is in the Mediterranean, in Toulon. And our 5th center is actually in the Pacific Ocean, in Tahiti. Along with these main centers, we have 20 marine stations located along the French coast and overseas islands. And you can see the name of the islands. For instance, there is a Réunion Island in the southern Indian Ocean, New Caledonia in South Pacific, Saint-Pierre-et-Miquelon, the North Atlantic, and in the Caribbean with Martinique, and also in South America with the French Guiana Center. To wrap it up, the originality of the institute lies in the conjunction of its diverse missions, approaches, and expertise. And here, IFREMER really covers a broad range of research activities and expertise. So we are organized in 4 departments. Just to go through the list, there are top-level teams that IFREMER work on ocean dynamics, physical and spatial measurements of the ocean are routinely collected and analyzed, then interfaced with the national and European data collection consoles. Global change is now at the center of ocean science issues, with an increasing interest on how to assess climate change multiple impacts on our coastal ecosystems and socio-economic human activities. The socio-economic system approach of coastal area is in line with IFREMER duties as regards public environment monitoring. So there are teams dedicated to surveillance networks of pathogens, chemical and metallic contaminants present in the marine environment. So these teams develop tools to monitor the good environmental status of coasts and seas. Teams are also involved in the marine ecosystem and biodiversity conservation. Just as an example, our IFREMER Center in La Réunion in the South Indian Ocean leads a long-standing project for sea turtles conservation. Ocean resources, living and minerals still need to be better comprehended, and IFREMER mobilizes technical assets to tackle these challenges with an ecosystem approach. This is really important for all our activity. Historically, IFREMER has always been very active in biosources products. We support technical engineering for the development of more efficient and sustainable fisheries, aquaculture, shellfish, and also pearl farming. This is the business in the Pacific Ocean. It seems to have know-how in control, capturing and bioconversion process of marine resources, such as algae bioconversions. Research are dedicated to characterize molecules of interest for the food, pharmaceutical, health, or beauty industry. Then deep sea exploration and mineral resources are gaining increasing focus at IFRAMER with our valuable know-how in geosciences and skills in geotechnics. The Institute also has very extensive means to explore marine environments, so we offer expert advice about seabed, either for sovereignty matters, like the extension of the continental plate, and also for offshore industries. And so many will produce studies for deep sea sites exploration and to detect, identify, and quantify deep sea mineral resources and assess the environmental impacts of such future operations. For instance, IFRAMER is a contractor for the International Seabed Authority on the Cameron-Clipperton port in the Pacific Ocean. As regards marine renewable energies, we also have some activity there, and mainly we provide knowledge and experience on the resource, like the currents, waves, ocean dynamics, and also provide some engineering methods for locating and characterizing renewable energy potential sites. We also assess the environmental impacts of offshore structures, modeling, tests, and behavior. So in this ecosystem approach, not to forget that the Institute has an overall mission to promote science in society and reach out to the community. So just let me introduce a little bit about the French oceanographic fleet. IFRAMER puts strong emphasis on technology at large. So a couple of years ago, the French Ministry of Research decided to mutualize the national research fleet operations for all French research institutions, including IFRAMER, but also CNRS, which is the National Research Center for Science, NIOT, which is our Institute for Research and Development, which is very present overseas, and IPEP, which is our Polar Research Institute. So in 2018, just 1 year ago, it has been created a national organization to manage and operate the fleet, which is placed under IFRAMER supervision. So we created a company for all these public institutions. The company is the owner of the ships and all the equipment on board. So this unified research fleet under the French flag is in the top 3 in Europe. So IFRAMER is the operator of these national seagoing vessels, also coastal vessels, and all the underwater vehicles and also instrumented platforms on board. So we have 6 deep sea vessels, in the Southern Ocean territories, Atalante, Atlasa, and also 2 vessels are positioned permanently overseas, in the Mediterranean, in the Indian and tropical Atlantic, and the Alice, which is a little old now, and which is based in New Caledonia, and which operates in the Southwest Pacific. We also have 12 inshore and station vessels, which have the responsibility to maintain the quality of the scientific and of support. So, being the main operator, IFRAMER has the responsibility to maintain the scientific equipment on the fleet. So we invest a lot on the technological developments in collaboration between researchers, engineers, and also sometimes private industrial partners. So within the fleet, our underwater vehicles include the NIOT, which is a manned deep water submersible capable of 6,000 meter deep dives with 3 persons aboard. We can directly observe the environment and the seabed surroundings. So since 1984, locomotive has accomplished almost 2,000 dives. And we also have Victor, our remotely operated vehicle, which has realized more than 700 dives. It's in operation since 1999. It's also 6,000 meter deep capable. Victor is specialized in scientific missions and is equipped with multiple sensors associated with high-resolution optical imaging. It can also generate 3D optical reconstructions of the environment that it is observing. And then on the bottom right, we also have Ariane. Ariane is a hybrid remotely operated vehicle. It has its own energy resources and an optical fiber connection to the surface. It can go down to 2,500 deep. Then we have our automated vehicles Asterix and Idefix, which are of 2,800 meter deep dives, and it operates since 2005 and in good synergy with the bigger other vehicles. So as I said, IFRAMER invests heavily also on testing facilities for research or industrial purposes. So we have a deep water wave tank in Brest, in Brittany, which is used for testing wave behavior, hydrodynamics of floating devices or underwater devices. So the tank is 15 meters deep. We also have a wave current circulation flume in Boulogne-sur-Mer. There is another tank not in the pictures in Lorient, which is mostly used for fishing gear tests. And of course, in Toulon, in the south, we have a test tank for underwater vehicles, the submersible base. Other facilities include pressure tanks, also marine sensor lab, mechanical test bench, and material labs. There's also an in-situ test station just next to our headquarters. Just to mention that we also joined resources with engineering school in Nantes, sometime Nantes, to pool our test facilities for hydrodynamics and marine renewable energy. IFRAMER also has several experimental stations on the French coastline dedicated to the study of fish populations, influence of environment condition on fish and marine organism life cycles, etc. So the two main sites are in Brest in the northwest and Palavas in the south. So you have here on the bottom a picture of Palavas station. This actually is the largest experimental facility in France dedicated to aquaculture and microalgae research. It's a joint structure, not only from there, it also has staff from NIOT, which are the National Research Research Institute for Agriculture, and NIOT for Research and Development, and CIRAD. So Palavas Station has indoors and outdoors facilities which are quite fit for integrated approach of aquaculture with projects to recycle industrial CO2 emissions and use microalgae for fish feed, for instance. To complete this overview of IFRAMER, lots of efforts are invested to bankerize data. This is really important to us. IFRAMER is strongly committed to develop interoperability and synergy with existing national systems and with a lot of partnerships with other institutes, for instance at national level with the CORIOLIS database, which gathers institute data in partnership between French research institutes working on ocean and earth sciences. So IFRAMER, the National Space Organization, CNRS, of course, also the Meteorological Service and the French Navy Hydrographic Service, also the French Polar Bear. So we all gather institute data in police. At European level as well, IFRMER is the main operator of the institute component of the Copernicus Marine Environment Monitoring. And for instance, we also are the coordinator of a European project, the CDataNet. As such, we promote common procedures and practices for water column data. And we share with all our European counterparts and users. At international level, IFRMER has a long-standing commitment to multilateral collaborations through the International Oceanographic Data Exchanges, NIOT, which is a program of the UNESCO IOC. Our information systems are also heavily involved in the management of data from several international programs in a variety of fields, such as physical oceanography with the Global Data Assembly Center, and also for biodiversity with the Census of Marine Life, as well as bathymetry data with the JETCO. To wrap it up, IFRMER ambition and vision is to foster research for sustainable ocean and the future we want. We are deeply committed to support the UN Decade for Ocean Science for Sustainable Development. We identified 6 ways forward for our institute. So first is to understand ocean dynamics and its future evolution towards the year 2100. To study climate variability and geological events and hazards. To study ocean-lithosphere interface. Also to enhance knowledge on biodiversity and ecosystem functioning. Also to better understand the evolution of organisms under global change. And of course to give close attention to the adaptive management of marine social ecosystems. We'd like now give a little bit focus on the observation of the ocean, which is a big thing in our institute, which is really inscribed in IFRMER's strategic planning to understand the ocean from the surface to the deep sea. And for that, research infrastructures are essential resources and services to foster innovation. So IFRMER dedicates significant workforce in supporting international research infrastructures in a wide array of topics for observation, ocean energy, underwater vehicles, aquaculture, environment, etc. And especially in observation infrastructure, which needs to be supported by fair data, as we mentioned before with our colleagues. It's important principles to operate information systems and infrastructure. And these observatories should address knowledge gaps and combine advanced models, and also play a key role to activate bilateral and international cooperation. In that regard, of course, you all know about the Argo international programs. IFRMER actually is a leader for the European chapter of the Argo network. We have been involved in designing the profiling flows for 30 years, and we have our own technological development team for the Argo flow. Still, nowadays, half of the ocean volume is not monitored by Argos, which so far goes down to 2,000 meters. And this is the reason why in the last 10 years, Japan, USA, and France joined efforts to develop new Argo float technologies to be able to observe all the ocean, including under ice, marginal seas, at full depths, up to 6,000 meters, and be interdisciplinary, in addition to temperature and salinity, which is now monitored by Argo. We can now measure biochemical variables. So we propose a deep Argo network. IFRMER is part of it via the Deep Argo project, that is the float picture, the Deep Argo. It's a new profiling float to extend the Argo observations down to 4,000 meters. which covers roughly 88% of the ocean's volume. So you can see on the map that deep cargo are deployed now in the southwest Pacific Basin. This is the blue dot. Australian Antarctic Basin and North Atlantic Ocean. So now we need international coordination and of course financial support to keep implementing and upgrading the operations. IFRA is also working hand in hand with international partners to deploy ambitious sea observatories. So it's the main projects around the world. Because we believe we need to develop new capacities and approaches to studying the oceans, which are fixed points to enable long range of observation over 10 years, and observation of the seafloor, sub-sea floor, and water column. So one example is ENSO. The ENSO project is a European network of regional observatories. Give now a quick presentation of IFRA presentation to it. IFRA contribution to ENSO. So ENSO stands for European Multidisciplinary Seafloor and Water Column Observatory. It's a European research infrastructure supported by the EU and involves 13 partners. So ENSO consists in a system of regional facilities which are placed at key sites around Europe. ENSO offers data and services to a large and diverse group of users. So the network provides monitoring of the environmental processes involving the interactions between the geosphere, biosphere, the hydrosphere, and natural hazards. So the scientific purpose is to develop long-term series, coordinated, real-time, high-resolution, and multidisciplinary, and of course open access data. So IFRA is a pilot team of the ENSO node, which is located offshore the Azores Island in the Portugal Sea. So the project was initiated in 1998. It's called MOMAR, for monitoring the mid-Atlantic ridge. It is focused on monitoring the Lucky Strike vent field, which was discovered in 1993 at 1,700 meters deep. So MOMAR is a seabed observation infrastructure. It's set up the Lucky Strike, the volcano. And so here, to describe the infrastructure, there are two monitoring nodes. One dedicated to seismic activity, and the other one is dedicated to all the chemical measurements and acoustic measurements. So acoustic and data is transmitted via satellite to a relay buoy, and from there to the ENSO data center. So IFRA team is in charge of interfacing observatory sensors and data assimilation. So to date there have been 9 MOMAR oceanographic campaigns. So the last one was this July. And for the first time for this maintenance campaign, there has been the no-till on board. So we're going to follow on the Facebook, so nice pictures. And also for information, if you're interested in that, with the next ENSO workshop taking place in France this September. So registration is open. To conclude, we wanted to convey the message that we believe that the ocean particularly needs a coordinated international effort. IFRA intends to be in a leading force to foster ocean resources, which means that we are able to leverage our bilateral cooperations. IFRA is really now very heavily involved to foster ocean issues at European level. We contribute to networks and to really act in a very European policies through different networks and alliances. At a global level, of course, IFMR takes part in major multinational research programs on climate, environment, biodiversity, and geosciences. And in line with these big political policies, priorities, IFMR advocates for the development of seabed mapping, the enhancement of routine, ocean observing, and transnational monitoring activities, which goes along with the improvement of global data sharing infrastructures. Well, thank you very much for your attention, and welcome to visit us.
Thank you very much for this quick tour. I have time only for a short question. If anybody has. Yes.
This is a compliment. You took us through the entire gamut of what all is happening, what you wish to do, what you want to do. So my compliments to you for such a beautiful talk and discussion. Thanks a lot.
Thank you very much. Thank you very much. We have to move to the last paper, which will be given by Dr. Misra from NRB.
Professor S.C. Misra received his PhD from University of Newcastle upon Tyne, UK. He has been a professor and head of the Department of Naval Architecture and Ocean Engineering in IIT Kharagpur till February 2009. He had taken over as Director of the National Ship Design and Research Center, Visakhapatnam. Currently, he holds the post of Director of Indian Maritime University, Visakhapatnam campus, under Ministry of Shipping, Government of India. Since taking over as Director of Indian Maritime University, Visakhapatnam campus, he has started undergraduate and postgraduate program in Naval Architecture and Ocean Engineering, and he is also the Chair of Naval Research Board. Professor Misra.
Good morning to all of you. First of all, I have this opportunity to stand here and congratulate NIOT for the 25 years of activity. Congratulations to you, all members of NIOT present and past, Professor Ravindran, Dr. Atmaram, and everybody else. I have been lucky to have been associated with NIOT for most of his life. I think for 20 years or so since I came to Madras in 1998. And it has been a very nice experience. And I feel proud to be a part of this organization in some form or other. I was given a topic to speak on modern ship design. I didn't know whether I had to stick to the topic or change it, but I stuck to the topic. Modern ship design is not a subject which you can cover in half an hour with some depth. So I am just going to present a few viewpoints which I think are important for design of large, complex structures of any kind. And this means I am moving away from R&D and technology demonstration, to which we have heard so much in the last, till now, since yesterday. And I will be moving on to design, which is the next step to technology demonstration. Does NIOT need some knowledge about design? I would think so. Ships are an integral part of any major activity that NIOT may do in the ocean environment. ships are expensive, and if this expensive platform doesn't perform as it was expected to do, then of course there are a lot of problems. I am aware of at least one vessel that NIOT had, I am just getting mixed up. NIOT had, Sagar Sampada, which had a small little problem, but for the scientists that worked on this vessel, it was a major problem. There are complaints galore that this vessel is not giving us comfortable scientific study environment. Something was done, the comfort level was increased. But my point of telling this here is that when a platform is made, if it was not designed and built properly, then there could be problems which may not be addressed at a later stage. It's an expensive system. If it doesn't work, it's really bad. So to this extent, design forms an integral part of any platform design or any complex system design that is to operate in the ocean environment. Now let's come to why do ship design in this country we know as India. Can we not buy ships from abroad? Of course we can. Can we not build ships to designs purchased from abroad? Yes, we can. If the answer is yes to all these questions, the next question comes, then why design? Why spend effort in designing a ship and building it as per the design? Before we start on the topic, I thought that I would address this question. I believe when you talk of a designing of a system, we design in stages. We do the designing in stages. The first step is what we call a feasibility study. We see whether such a thing is feasible to make or not. Then we do something called a concept design, where we broadly fix the parameters and say that this can be built and this can be manufactured within certain cost parameters. The next step is what we call basic design, and then we come to detailed design, to which the item is manufactured. Now when we buy a design, we normally come up to the basic design stage and say, can you provide me this up to this design stage, the design drawings, documents, specifications, and I can build it. Then you come to the shipyard and say, okay, this is the design I have purchased, can you build a ship to this? The shipyard's job it is to produce a detailed design, or sometimes it is called the manufacturing design, to which the ship is built in the shipyard. Now there are a number of problems that come up during this process, and then there are problems. If the design was built, if the design was done in-house, these problems can solve automatically. I'll go to the next slide. Who do we design the ship for? Do we design the ship for the builder? Let's understand what is the builder's objective. Builder's objective is to build a ship at low cost and make a profit. Or do we build it for the owner or the operator? In this case, NIOT. Should we be looking at low operating cost, low lifetime cost for a specific lifetime of the product? Or is it possible to build a ship to a design in an effective manner such that both capital expenses and operating expenses are low? capital expenses, which is normally called capex. This term I came to know very late in my life, but I believe it's a very common term. So the capex is coupled with financing. Whether it's government financing, private financing, or whatever it is, capex forms an important part. Can it be afforded by the client to provide this money to purchase the ship? OPEX, on the other hand, is also very important because that determines whether it is possible to operate this vessel within certain cost parameters. Look at Indian shipbuilding. Two things we keep hearing all this. High cost of construction and large delivery. Indian shipyards build ships for a very long period. There are frequently time overruns as well as cost overruns on contracted values, and there are excuses galore, and there are conflicts between the owner and the builder. And in this process, please understand that the product suffers. The product, which is a high value product, is not able to be utilized for the purpose it was built. I must mention at this stage that very recently, about 2 days back, 3 days back, NIOT took over a vessel from Chicago Wagons Limited, Sagatara, which has been mentioned. In fact, a small video clip was shown in the presentation done by Dr. Atmaran. This vessel was delivered before time and without any cost overrun, with some additional facilities. I am very proud to have been associated with design and construction of this vessel. My point of telling this at this stage is that it is possible, if there is a way, if there is a desire to build ships reasonably within a fixed price and perhaps within a fixed time frame. Okay, with this, can we look at the various design activities that one goes through while designing a ship? I spend 2 minutes on this slide. Market study, market forecast, and technology forecast. All this is fairly well known except the last item, technology forecast. Situations have changed drastically since last 20-30 years. Technology is something which is changing almost daily today. So technology forecast, see, when we are building a ship, building a platform, we are talking of the platform being delivered to us maybe some 3-4 years later. What would be the technology then? Would it be really applicable? Am I incorporating that in the design? That's something which must be taken into account. Then we can talk about the technical design, the shape and size, hydrodynamics. We have learned a lot about hydrodynamics today. And in case of ships, we talk of something called computational fluid dynamics, which is very frequently applied to ship design today, to design the hull form, to design the propeller, to design the underwater appendages, so on and so forth. We also talk about maneuvering of the ship easily with the use of a rudder, with the use of thruster, or ABP system. All these are hydrodynamic studies. We also talk about how comfortable is the ship to work on, such as the roll motion, the pitch motion, the heel motion, etc. Structural layout and design. Today, in today's environment, we are talking about reliability. We are talking about platforms lasting for 15 years, 20 years, 25 years, or even longer. So can the structural reliability guarantee us that? Finite element methods of structural strength analysis have formed a regular part of ship design process. Reliability studies, fatigue analysis, and lifetime reliability is now form part of design. Machinery, again, compared to what we talked about, what we learned maybe 30 years back. Today machinery has become a variable. I remember when I studied naval architecture some 50 years back, we had only the slow-speed diesel engine as one item that must go into the ship, which meant that there was no alternative. It was not a variable. So I didn't bother about it. I just buy the engine and put it. Today we have many alternatives of machinery. We have electrical power systems, we have battery operated ships, we have LNG operated ships. And tomorrow maybe we'll have solar, wave and wind energy powered ships, maybe hydrogen fuel cells. So machinery itself has become a design variable, and that must be understood by the designers, that you cannot really talk about only shape and size and hydrodynamics. Machinery itself is a design variable. Space and volume, weight and stability. I'll bring in a point here. Many ships built in this country, after they're launched, it is frequently found that the weight has overrun and the vessel has become slightly imbalanced with regard to port and starboard side. So in design, perhaps it is now necessary to incorporate a method of checking weight and balance during the stage of construction. This I have been stressing in my lecture classes in design, and I believe that this must form a part of normal design activity. Building cost estimation. I mentioned about pricing, financing. That's a major function of that is the building cost estimation itself. Can it be afforded? The client would normally say, I have so much money, can you give me a ship? Perhaps that should find a way into designing the product. Operating economics, I mentioned it before, that's very important. Then we have manufacturing design, steelworks and procedures, assembly procedures, estimation of work content, and production information generation. These are all very advanced today, and this should be utilized. Finally, we come to a thing called sustainability. Energy efficiency, we have heard about it. IMO is very much concerned about energy efficiency, and they have laid guidelines now for energy efficiency, something called EEDI, Energy Efficiency Design Index, and Energy Efficiency Operating Index, which must also be calculated at the design stage to ensure that the operation is being done properly during the lifetime of the ship. Use of alternative energy sources, we have heard a lot about it today. In ships we have the LNG alternative immediately available, but LNG perhaps will not last for more than 20-30 years. Then we will have to talk of other energy systems coming into ships. Design of safety during construction and during operation. Design of protection of environment. This is an important item. We heard about the environment only in the last lecture. Ships cause a lot of environmental pollution. We have learned, IMO has set guidelines about SOx emission and NOx emission and also carbon dioxide emission. Apart from this, ships do pollute the sea through oil discharge is almost completely controlled now, but ships pollute the sea through ballast water exchange program. I am sure most of the audience here will be knowing what is ballast water exchange program and how migratory species are moved from place to place and they grow into quantities that cannot be controlled or they vanish. The painting system, which causes fouling on shipboard. Fouling is a system by which a lot of migratory species again get transplanted. Something has to be done about things. Something has to be done so that migratory species don't house themselves in the barnacles and get transported. Protection in environment, while talking about another item which is last, dismantling, IMO now is very much concerned about dismantling of marine structures. I do not know, so much of talk has gone into developing large structures at sea. Have we really considered how to dismantle them? I think this is an issue when you go from technology demonstration to implementation. This issue has to be addressed. You cannot ignore it anymore. Dismantling for ships, guidelines have been laid, but other marine structures, I do not know. I think this has to find a way into design of the product. Okay, with all those design activities, how do we go about doing it? Perhaps we can talk about CAD modules, generating graphic simulations for shapes, sizes, and distribution of spaces inside the shape, which will go into analysis module, CFM, CFD, FEM, and other software packages for doing various analysis can be done. We are aware of the pre-processing and post-processing for simulation of results, so that one can visualize what will happen when the ship goes into service, and perhaps some decision module where we can utilize MADM or MODM techniques and finally get a solution for various components of the design and the design as a whole. And if the solution is acceptable, go ahead. Otherwise, designing the iterative process, perhaps it has to be done. Before I go to this slide, I must mention when we are talking of only yesterday when I was talking to Dr. Naik, he mentioned to me that MOES is likely to acquire 3 ships. One is the replacement of Sagar Nidhi, I think he said, and one fishing research vessel, and another vessel, he didn't mention which one, but 3 vessels are to be acquired by MOES in a recognizable span of time. And he asked me, could we not have the same Alcom with perhaps the same engine operating to do for all the 3 ships. This is something fantastic coming from a bureaucrat. I was really amazed. This is something we have been talking about. Can we standardize? Can we rationalize designs? So that we can have a number of ships coming out of modularized concept of ships, ship hull as a whole module or ship hull as a part module, and fixing different things, and we get different ships, different platforms. And with regard to that, we have done some work at IIT Kharagpur and later at IMU Vizag. I'll just give you one example. You can see the front end of the ship. There are 2 different bulbs which have been fitted in the front part. You can see the line L1 which divides the hull, the front part, and you can also see the draft marks. A container ship would normally have a lower draft and a bulk carrier will have higher draft, and this forend is designed to provide speeds, optimum speeds for both these vessels in the same Alcom, speeds varying from 14 to 17 knots. And also you can have a variation in the midship region by extending the parallel middle body for a longer length and otherwise shorter length. This I am showing you, this is normally called as design for production. Can I modularize the ship? Can I have rationalization of equipment? Can I have, I will show you the next slide. You see, these are the variations that can come out of the slide I showed last part. Please observe that not only the forebody has 2 alternatives, the aft body is same, and perhaps it could have the same engine also. So if this can be done, then you can imagine the cost, the time and cost overrun both will come down drastically. So this concept has been patented and it is available. Next item, which is very important for designing, is innovation. We have heard about innovation. Innovation is the act of introducing something new which didn't exist before. This means thorough analysis of its design and application. The innovation, it may be small, it may be large, but it will affect. So, the analysis must be thorough, defects identified, and but by its very definition, innovation includes accepting risks of failure of new concepts. There must be a readiness to accept failures. Thus, innovation includes creativity as well as associated risks. Challenges for this. To maintain status quo is easy. This I just talked to somebody. Easy and comfortable. Let's run the things as they are going. No change. It's easy and comfortable. So why innovate and change? The reason is the obvious that we are comfortable with is may not always be right or the best answer. Constantly challenge status quo. Young minds should always constantly challenge status quo. Think out of the box. Never accept constants as God given. Often blocks are only in our minds. Innovations, major innovations in ocean environment. Everybody is aware of the top side, the bottom right side, wave energy device. You can, tidal energy device, and look at the bottom left side in ship design. This is developed by Ulsten back in 2006. It's called XBOW. So similarly, there can be large innovations and there can also be small innovations. I have one more point to tell, then I'll close. Design integration. Again, Dr. Naik told about this yesterday in his lecture, talked about system integration. When we are talking of a design of a product, it's normally a part of the overall system. Unless we can think of the system and how the product fits into the system, the product may not serve its purpose. Also, the product design itself consists of various items. Can they be integrated properly? Can hydrodynamics be integrated with structures? Can it be integrated with general alignment? Can it be integrated with propulsion? Many times it happens that this integration is not done properly. So there is a mismatch at the time of construction and the time of trials. This must be avoided. The design of multiple parts functioning cohesively and in harmony is called design integration. The whole is always greater than the sum of individual parts. So there is this slide, and I have got one more slide to show. There are various activities shown in the vertical arrows, and you see there are a number of cross-functional activities such as business needs, performance, sustainability, research and development. All this must be done. The design process includes all this, including the cross-functional activities, and that is done by something called design management. Same thing shown in a different form. You can see that knowledge base forms an integral part of this design activity. I will not undermine it. And also, you will understand that management of this activity is a very important part. I have been associated with two projects with NIOT. One is the 10 MLD project, which has gone through the DPR stage. We have gone through this integration, at least the inside part, very well. And second one, where we have gone through the overall integration, in the coastal research vessel design, construction, and delivery. And I'm happy to say both these projects have been done very successfully. Finally, a slide like this, I have taken it from somebody else. Look at the line diagram on top. A child can be asked to color it, and the left-hand slide, bottom slide shows the color, and the right-hand slide shows the integration between the various parts. That's what system integration is all about. It's applicable to art, it's applicable to science, and it is also applicable to ship design. Thank you. Oh, sorry, I got 2 more slides. No. Okay.
We have to stop, sorry.
Fine.
Time for a short question because I have to go to pee.
Good morning, everyone. Thank you, sir, for the wonderful talk, as always. And I have a couple of questions. Do you consider flap rudder design and anti-roll tank designs, and do you categorize under modern ship technology? Because I have been hearing this for quite some time.
Anti-roll tank design,
And flap rudder design.
flap rudder design. Yes. What is it? What is the
I just
question?
want to understand, does these two come under the modern ship technology design, or, because it's mostly it's a traditional kind of a design which...
Yeah, I'll answer this.
Okay, thanks.
Both flap rudder design and passive roll stabilization tank design are very well known. But they are not well known in this country. I am not aware of any design development with regard to these 2 items having done indigenously, introduced, and successfully installed. That has been done in the coastal research vessel. So it is not really an innovation in the true sense of the word, but it's an innovation in the in terms of installation. I would say installation, design, tank testing, etc. are known, but installation, manufacturing and installation, yes, it's new. To that extent, it is innovative.
Thank you very much, and thanks for all speakers for this session. Thank you. And we have to move to Mantan Hall for happy.
Sir, before that, I request you to present memento to the speakers of this session. Professor Yasuki Ikegami. We will continue with the technical session at 12 o'clock.